All right. 1.2 gets us into more data and sampling and how we get that information. So let's look at it. So we have two data types we're going to deal with, qualitative and quantitative. So if you remember from 1.1, qualitative is our categories. It's usually more words or descriptions. And then quantitative is your numbers. Typically, it's easier to analyze numbers. There's more you can do with it. You can put them in calculators and spreadsheets. Sometimes other ones are qualitative beneficial, but usually we're going to use quantitative in the world of statistics. These are numbers from counting or measuring. Well, I'm not going to write that right there. Numbers. Discrete numbers are countable. Whole numbers, you don't have parts of things. Continuous, you get from measurement. That's where you have your decimals and fractions. Anything you can measure, you can always break down. So think, if you have a mile, you can have half a mile. If you have half a mile, you can have a quarter mile. If you have an inch, you can have half an inch. You can have a quarter of an inch. It can always get smaller. That's what makes it continuous. Countable, like you can't have half a shoe because then it's not a shoe. That's kind of the easiest way to think of the difference. So let's look at example 1 here. Is the data discrete or continuous? The number of books a student can carry in your backpack. This would be discrete because you can't have half a book. If you have half a book, then it's useless to you, so it doesn't count. It's not really a book anymore. So that would be discrete. Weights of a backpack is continuous. Because if you stuck it on a scale, depending on the accuracy of the scale, it might be 15 pounds. It might be 14.9 pounds. It might be 14.86 pounds. So you can always get more accurate with measurements, so that makes it continuous. So why don't you try number 1? Is it discrete or continuous? The number of machines at the gym. So that would be discrete. If you only have half a machine, it's not a machine. Area of the lawn in square feet would be continuous because that's a measurement. You can always get more specific. All right, now we're going to look at it from a different lens. You go to the supermarket and purchase 3 cans of soup, 19 ounces tomato bisque, 14.1 ounces of lentil, and 19 ounces of Italian wedding. 2 packages of nuts, walnuts and peanuts, 4 different kinds of vegetables, broccoli, cauliflower, spinach, and carrots, 2 desserts, 16 ounces of pistachio ice cream, and 32 ounces of chocolate chip cookies. Name a set that is quantitative and discrete. So one set that would be quantitative and discrete would be the number of cans of soup. Number of cans, 3 cans. You can't buy half a can. The number of vegetables. 4 vegetables. Those are a number of discrete, right? Name a set that is quantitative and continuous would be the amount in a can. 19 ounces, 4.1 ounces, or the mountain ice cream, 16 ounces. Weight. Name a set that is qualitative. That would be like your type of nuts, type of soup, type of dessert. Walnuts and peanuts, broccoli and cauliflower. Those are your qualitative data points. Hopefully that helps, because you're going to try it now. So pause the video, see if you can answer this one, and then check back in. So name a set that is quantitative and discrete. So that could be your number of types, 2 types of nails, 1 type of oil, 4 types of screws. Name a set that is quantitative and continuous. So that would be the weight. 2 kilograms of nails, 3 kilograms of roofing, 4 liters of machine oil. And then name a set that is qualitative would be your item or your type of screws. So wood screws, machine screws, roofing nails, type of oil, machine oil. Those would be the qualitative pieces. All right, let's look at this. Determine if the data is quantitative or qualitative. If it is quantitative, go the 1 step further and say if it's discrete or continuous. So color of backpacks. So color is a quality, so it's qualitative. The number of pairs of shoes, that would be quantitative. So since it's a number, we keep going. And then pairs of shoes would be discrete because you can count them. It's either a pair or it's not. The type of car you drive would be qualitative. The distance from your house is a measurement, so that's a number, quantitative. And measurements are continuous. And then IQ scores are numbers, so that's quantitative. And the numbers mean something, quantitative. And all IQ scores are whole numbers, so those are going to be discrete because IQ scores are whole numbers, in case you didn't know that. All right, so why don't you pause the video and try the U-Try. Determine if it's quantitative or qualitative. If it's quantitative, determine if it's discrete or continuous. So color is qualitative. The number of classes is quantitative. And you usually don't take half a class because if you do, it doesn't count. So that would be discrete. The type of calculator is qualitative. You have a scientific or graphing or one line, whatever you want to call them. Weight is a number, so that's quantitative, and it's a measurement, so it's continuous. Number of correct answers is quantitative, and typically you count like 1 or not, so usually it's discrete. Sometimes you get partial credit, like so you have 1.5 correct. But there is a limit to how break down. So, I mean, I would take continuous if you defended it. Like if I marked it wrong and you said, hey, but you give partial credit, so that counts as breaking it down. So if you could defend that to me, I would give you the point back. But usually you would say, you know, it's discrete because it's either right or wrong. So that's one where as long as you could defend yourself, it could go either way. All right, let's look at this. This is a circle graph or a pie chart. Statistics professor collects information about the classification of her students as first-year students, sophomores, juniors, or seniors. The data she collects are summarized in the pie chart below. What type of data? So if we look at this, the way it's given, first year, sophomore, junior, seniors, those are qualities, right? They're not written as numbers, so it's qualitative. There's no numbers on this graph. So why don't you try this one? The registrar at the state university keeps records of the numbers of credit hours students complete each semester. The data collected are summarized in the histogram below. Class boundaries are 10 to less than 13, 13 to less than 16, 16 to less than 19. So these are all numbers of credit hours. Numbers are quantities. And then if we were to go 1 step further, numbers of hours would be discrete. It didn't ask you that, but if you chose to do that, that's what where we went. All right, let's check out the next one. All right, data displays. So once you have that data, how can you look at it? So percents can be helpful when your sample sizes are different. So if you're trying to compare a couple samples, one sample had 25 people and one sample had 100 people, if you just talk about the number of people, it doesn't necessarily mean anything because one sample is a lot smaller than the other. So percents can be helpful. You look at what part of each sample. So that's a good thing to look at. Different graphs might be helpful in different situations. So depending on what you're trying to convey or what you're trying to look at, different graphs might be helpful. So we're going to learn about multiple different types of graphs in this class. So a pie chart shows categories represented by proportions or percents. So that's a way to compare different percents. A bar graph, oops, that didn't work. So pie chart, we just saw one. Pie chart looks like this. Bar graph looks like this. So bar graph, the length of each bar is proportional to the number or percent. You can do it either way, numbers or percents, of individuals in each category. Some are vertical, which is up and down. Some are horizontal, which is across. Doesn't matter. Be careful when you're looking at it. Sometimes the percentages can add up to more than 100 if items fit in more than one category, or if someone's trying to mislead you. Pie charts can't be used if the total is more than 100. Sometimes percentages don't add up to 100 because a category was left out or people didn't answer the question. Pie charts can't be used if the total is less than 100. Pie charts can only be used if it's 100%. Sometimes there's a category that's like other or unknown. Well, if you don't know what it is, that can skew your results. So you always want to pay attention to the whole picture, not just the pretty part. Pay attention to what you're being shown and what you're looking at and what you're displaying to make sure you're showing accurate information. Sampling is how you get your information. There are different ways to get your samples, and depending on how you do that affects whether you have a good sample or a bad sample. Sometimes you can do everything right and still get a non-representative sample. Your goal is to do your best. So the sample should have the same characters as the population, and the sample affects the results. So if you end up with a poor sample, your results may not give you the right predictions, which if you're trying to make things based on money or print newspapers, it could end up costing you things. So your goal is to do the best you can if this ends up being like a career for you. We're going to talk about some different ways to get samples and what's good, what's bad, things like that. So random sampling is when every member of the population has initially an equal chance of being selected for the sample. So simple random sampling is the most basic. Every member has an equal chance. So that's putting names in a hat. You take every single person in the population, put them in a hat, shake it up, pick them. You can use a random number table. So there's ways to put random numbers on a table, start in a random place, and then go through the table. You can use a random number generator. There's things on the computers you can do now to like randomly pick names. The calculator will do this for you. So your graphing calculator will actually do this for you. It's often the simplest if you already have a list rather than making random tabs or typing things in. So I'm going to show you on the graphing calculator how to do this. So over here on the left under the green button, there's a button that says math. So if you hit that math button and then arrow over to where it says PRB, that means probability. So use the arrows to go over to probability. And then go down to number 5, which is random integer. That's what that means, rand int. So scroll down to number 5, hit enter. Then you're going to answer the questions it asks you. So it asks you your minimum, which is going to be the lowest number. Then it asks you the maximum, which is your highest number. And then it asks you N is how many to pick. So let's say we have 100 things and we want to pick 5. So we start at 1. That's the first number on our list. It goes up to 100. Oops. Math, probability 5. Start at 1, go up to 100, and we want it to pick 5. These are the 5 numbers it's going to tell us to pick. On that list, we're going to take the 91st, the 15th, the 52nd, the 41st, and the 74th. Now we have our random sample. So if you have a list, that does it for you. So that's how you can do that with a calculator. That's one way. That's simple random. Okay. Another way is stratified. So divide the population into groups and then randomly take a proportionate number from each strata. So if we think about university, we have different majors. Then within each major, we take a sample. So we want to make sure we get opinions from every major. Larger majors would have larger samples. So maybe at the beginning, there's a lot of people who are undecided. Or maybe there's a big chunk of people who are just taking a one-off class, and that counts as one of our majors. So we take everybody from aviation majors, everyone from business major, everyone from nursing major, everyone from undecided. We figure out what percent of the school it is. And then, so if nursing, and I'm making these numbers up, if nursing was 15% of the school, and aviation was 30% of the school, and business was 10% of the school, then we would take all of the nursing majors, and we would want, if we were asking 100 people, and nursing was 15%, we would want 15 people from the nursing majors to be in our sample. And I think I said business was 30%, then I want 30 people out of the business majors. So we want the percent of the whole population to match the percentage of our sample. So stratified, divide the population into groups. We chose to do by majors. And then take a sample, a simple random sample, from each group. Then that becomes your big sample. If you think back to like high school, maybe you go to the lunchroom and each table is one of the groups. And then you go take a sample from each table. Ask a person or two from each table. And that becomes your sample. That's a stratified sample. Cluster is similar in that you break it up into the groups, but then you take a random sample of the groups and ask the whole group. So instead of asking some of each group, you're going to ask some groups, but the whole group. Sample entire group. Some groups. So if we did the majors, I put all the majors in a hat, and then I'd pick like 3 majors and ask everybody in those majors. If I went to the cafeteria, I'd pick like 3 tables and ask everybody at those 3 tables. So when you're doing that, the difference between the stratified is if your clusters are, if your groups are homogeneous, or if they're grouped by a certain way, the stratified, you're going to get some from every group. With the cluster, if everyone's kind of spread out, then asking the whole group, because everyone's mixed, heterogeneous grouping, if everyone's mixed, then you get everybody all at once. If we were to do the cluster grouping with the majors and we only ask nursing and business majors, we're going to leave out everyone that has anything different than nursing and business. So you have to think about when you're grouping which one's helping you represent the population. If you only ask nursing and business majors, you're not going to get anyone that's not like sciencey, mathy kind of thing. You're going to leave out anyone that doesn't think that way. If you don't get a cluster that's different from them. So some are better than others depending on how your groups are. It all depends. All right. Another way is systematic. So you randomly select a starting point, and then you take every nth piece of data from the list. So the benefit of this is you don't need a list, a full list. So one good thing is, like, if you stood at the door and asked every fifth person that walked in, because there was only one door to the building, you asked every fifth person that walked in until everyone was there, then you'd have, that's a systematic sample. It's random because you don't know what order they're going to come in the building. They come in different every day, so that's why it's random. And by asking every fifth person, you've spread it out. You've gotten the early comers, the late comers, the people that come on time. And you don't need to know everyone that's on the list ahead of time, because even if they're not on the list, you can add them at the end. They're still every fifth person. So that's what a systematic is. Like, you pick a place to start. Starting at number 10, I'm going to ask every fifth person. That's systematic. And then convenience is not random. It's easy to get. It's often less expensive. The downfall is it's not random. So because it's not random, it's often not as valid. These are things like mail-in surveys or voluntary, or you just ask whoever's right next to you. Like, I'm sitting in this classroom, I'm going to ask these people. Yeah, they're easier to get, but because they're easy to get, they're less representative and they're not random, so they're less likely to be beneficial. Sometimes you get lucky and you happen to have a really good sample, but that rarely happens. So we're going to look more at those in a few minutes. First, let's talk about errors. So sampling errors is when you get an error in your data caused by the process of getting a sample. So that might be the convenience sample. Or that could be, maybe I did cluster sampling and I ended up with clusters that were so similar, I left out a chunk of the population. Non-sampling errors are caused by other factors. So maybe there was a malfunction in the data. Maybe I did like a data entry error wrong. So that's any other kind of error in my data collection that wasn't from the process of the sampling. And then sampling bias is when you did everything right, but the sample isn't representative. So your process was all correct, you did everything fair, and then somehow your sample just wasn't representative and led you to incorrect results or predictions. All right, now let's go work with this information. Okay, so we need to make sure our studies are strong. So to have a strong study, you want to make sure you have a representative sample so you don't lead to the wrong conclusions. You want a good sample size. if it's too small, it could be unreliable. Who asked the questions? So you need to be careful of interviewer influence. If a boss is asking questions about the place of work, people might not answer as honestly. They might, you never know. But just, you want to be careful of who is interviewing. Who responded? Is there a group missing? Or is there a group overpowering? If you look at your respondents and you're like, no women ages 20 to 30 responded. Maybe something happened there, or what happened there. Just things to think about in your study. Who funded the research? Who is benefiting from the research? Who benefits? So if we're doing a study on ChatGPT and ChatGPT funded the research and all the research says ChatGPT is great, that should give you some pause in the study. It may be fine, but it may not. Is the data clearly presented? Is it complete? How are the graphics? Are you missing anything? You want to look at all of those pieces, and then are all the variables considered? There's this thing called confounding, which we're going to talk about. Are there multiple factors that are targeted? Multiple variables? All of those things have to be considered to decide if a study's strong. If we've only taken a sample of 5 people, but everything else is good, it might not be a good study. So you want to look at all of the pieces before you can decide if something's really good. You can have a strong study, but if you only asked 15-year-old boys, then is it valid? You have to think it could be. It depends on what you're studying. If you're studying how 15-year-old boys act, then yeah, you only want to ask 15-year-old boys. You just have to look at all of the pieces. So let's look at this example 5. And we're going to go back to those types of studies. We're going to say, hey, is it simple, random, stratified, cluster, systematic, or convenience? Study is done to determine the average tuition that San Jose undergraduate students pay per semester. Each student in the following sample is asked how much tuition they pay per fall semester. What type of sampling is used? So A, a sample of 100 undergraduates in San Jose is taken by organizing students' names by classification. First year, sophomore, junior, or senior, and then selecting 25 students for each. So they put them into groups by year, and then pick 25 from each year. So first you put them into groups, and then you take some from each group. That's stratified. Help if I could spell. Stratified. Okay. B, a random number generator is used to select a student from the alphabetical listing of all undergrad students in the fall semester. So they're all in a list. Starting with that student, every 50th student is chosen until 75 students are in the sample. So you start somewhere, and then you go every 50th. So as soon as you see that every 50th, that tells you it's systematic. Okay? Completely random method is used to select 75 students. Each undergraduate student in the fall semester has the same probability of being chosen at any stage. So that's just simple random. Okay? The first year, sophomore, junior, and senior years are numbered 1, 2, 3, 4. A random number generator is used to pick 2 of those years. So they're put into groups. You pick 2 years, and then all students in those years. So because you're doing all students in 2 of the years, that's cluster. So group, And then you do 2 of the full years, you cluster. And then an administrative assistant is asked to stand in front of the library one Wednesday and to ask the first 100 undergraduate students he encounters when they paid for fall tuition. Those 100 students are the sample. So when you just stand somewhere and ask the first 100 people you see, that's easy. So that's convenience. So those would be the 5 types. All right, you try. Pause the video, try them, see how you do. Okay, let's see. A soccer coach selects 6 players from a group of boys, 7 players from a group of boys aged 11 to 12, 3 players from a group of boys aged 13 to 14. So 3 groups, different amount of players from each group. That's stratified. A pollster interviews all research human personnel in 5 different companies. So all people in multiple companies is cluster. High school educational research interviews 50 public high school and 50 private high schools. So you have 2 groups and some from each. That sounds like stratified. Okay, a medical researcher interviews every 3rd cancer patients from a list. So every 3rd is systematic. High school counselor uses a computer to generate 50 random numbers and then matches those. So that's just simple random. Student interviews classmates in their algebra class to determine how many pairs of jeans students wear. So if they're just in their class, that's convenience. Okay, convenience. Oh, that word's so hard to spell. I think that's good. Okay, let's see what we got here. All right, now let's try making some samples. So you're going to use the random number generator in the calculator to generate some different types of samples. The table displays 6 sets of quiz scores. Each quiz counts as 10 points for an elementary statistics class. So create a stratified sample by rows. So that means this is group 1, this is group 2, group 3, group 4, group 5, group 6. So those are our strata. Pick 3 quiz scores randomly from each row. So I'm going to hit, so there's our rows. Stratified sample by rows. Yep. 3 scores from each row. So I'm going to number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So number rows 1 through 10. Then I'm going to do the math. Go over to probability. And I want to pick 3 scores from each row. So number 5. So my minimum is going to be 1. My maximum is going to be 10. And I want to pick 3. 1. What is going on? 1. 10. 3. So 1, 4, and 10. So for the first row, 1, 4, and 10, my scores are going to be 5, 9, 8. Then I do it again. So I'm just going to hit enter, enter. 3, 8, 10. 10, 8, 8. Hit enter, enter. So repeat for each row. All right, 3, 4, 1. 3, 4, 1. 10, 8, 10. Enter, enter. 10, 2, 1. So 9, 8, 9. Enter, enter. 6, 9, 10. 8, 7, 8. Enter, enter. 3, 3, 2. 3. Well, we picked that one twice, but that's okay. 3, 3, 2. So 6, 9, 9. Now, that one happened to pick the same one twice. I think if I do math probability, if I pick 8, number 8 instead of number 5, it won't repeat that number. So either way is fine. It doesn't say don't repeat, so it doesn't matter. So that's one way to do a stratified sample. I've picked 3 from each group. Now I have a sample of numbers. All right, let's look at cluster. So picking 2 of the rows. So the rows are numbered 1 through 6. So if I do math, go over to probability, choose number 5. We're going to start at 1, go to 10, and I want to pick 2 rows. So start at 1, go to 6, not 10. Sorry, there's 6 rows. And I want to pick 2. So 1 and 5. So that's my data. 1 and 5. So I'm going to write all of those numbers down. 5, 10, 9, 9, 7, 9, 7, 8, 9, 8. And then down to row 5. 8, 7, 7, 8, 7, 8, 8, 8, 7, 8. That's my cluster. Okay. Simple random of 15 quiz scores. So I could number these boxes. Start here with 1 and go all the way up through 60. So number 1 through 60. And then pick 15. So then I'd hit math. Go over to probability. Pick, this time I'm going to choose 8. So I do the no repeats. So math, probability, choose number 8. No repeats. Start at 1. Go to 60. And I want 15. So number 1 is 5. Then it says number 26. So 10, 20, 1, 2, 3, 4, 5, 26. 19. 59. I know there's 10 in each row, so I can count by tens. 2. 51. So 10, 20, 30, 40, 51. 38 will be here. 13, 60, 40, 1, 2, 3, 4, 15, 57, 56, 3, and 7. There's my random numbers. And then a systematic sample of 12 scores. So I'm going to do random integer, pick 1. So I'm going to do the same thing, 1 through 60. 1 through 60. Math. Prob. 5. Pick 1. That's going to tell me where to start. So I'm going to start at 42. Uh, 42. So I'm going to start right here. And then I'm going to pick every 6. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I just went back to the top when I ran out. 1, 2, 3, 4, 5, 6. How many is that? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. That's number 8. 1, 2, 3, 4, 5, 6. That's number 9. 1, 2, 3, 4, 5, 6. That's number 10. 1, 2, 3, 4, 5. I'm just going to skip that one. 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So I'm just skipping them the second way around. 2, 4, 6, 8, 10, 11, 12. Oh, I have 13, so I guess I didn't need that last one. There's my 12. So there's different ways to do that. If we all did these separate times, if you put them in your calculator, you would have gotten different numbers. It's because they're random. So everyone's calculator is going to get different numbers. For number 4, we'd all would have started in different places. You might have chosen a different number. You might have counted by 10 instead of 6. You might have counted by 5. That's the benefit of the random samples. So that was an example of how you can use the calculator. How doing the same thing, we have different ways of doing different samples. They're all different. And then depending on what we do with those data sets, we can get different answers. Okay, let's look right here what we've got. Suppose ABC College has 10,000 part-time students. That's the population. We're interested in an average amount of money a part-time student spends on books in the fall term. Asking all 10,000 students is an impossible task. Suppose we take 2 different samples. It is unlikely that any student is in both samples. First, we use convenience sampling and survey 10 students from a first term organic chemistry class. Many of these students are taking first term calculus in addition to organic chemistry class. The amount of money they spend on books is as follows, and there's a list of numbers. The second sample is taken using a list of senior citizens who take PE classes and taking every 5th senior on the list for a total of 10 seniors. They spend that number of classes. Do you think that either of these samples is representative of the entire 10,000 part-time student population? I'm going to say no. The first one was more of a convenience sample because they're all in the same class. And calculus and organic chemistry are typically more expensive. Unless those professors have all found Openstax, those are expensive books. And then the second one, although it was a stratified sample, PE is less books, right? They're limited groups. They're less books. They're not representative of the population. The whole 10,000 students are not half senior citizens taking PE and half students, first term seniors taking organic chemistry and calculus. They're not representative of the average student. Representative. Okay. Since they're not representative of the entire population, is it wise to use the results to describe the entire population? No. As soon as you know you're not representative, you're biased, so you should probably get a different sample. Is the sample biased? Yes. When you're not representative, you're biased. All right. So pause and try the you try. A local radio station has fan base of 20,000 listeners. The station wants to know if the audience would prefer more music or more talk shows. Asking all 20,000 listeners is almost an impossible task. The station uses convenience sampling and surveys the first 200 people they meet at one of the station's music concert events. 24 people say they prefer more talk shows. 176 people say they perform more music. Do you think that this sample is representative? So, the first thing I'm going to point out is it's a station music concert. So if you're asking if they perform music or talk shows at a music event, you're probably not going to be representative of your whole crew. You're probably going to have more music people. It could be, but it's probably not. And the fact that they tell you it's convenient sampling. That right there tells you it's probably not. All right, the last thing we're going to look at in this section is the variation in the data. Changes in actual measurement. So when you're dealing with like ounces in a soda can, like can say 12 ounces or 16 ounces, that's not actual. It's 100%. Like machines have set guides to stay in. Like they're supposed to be within maybe half an ounce or a quarter of an ounce. I don't know exactly how close they're supposed to be. It's probably not that close. So there's actual variation in that. Every can is not 100% exact. You're sampling members. You're asking different people. You know, if we go back to the page we just did with the calculator, where every time I do that, I get a different sample. Those numbers are different than the numbers in my notebook because it's random. So every time you go out and get a sample, if you ask a group of people, and I did it again tomorrow, I had to get a different group of people. All of these things cause variation. That's why data is never perfect. The response could be different on a different day. Sometimes people feel different. They think different. They're in a different mood. Your sample size. The larger your sample, the less variation, because you have more overall data, so it covers more of that variation in it. So if you have less variation from the sample to the population. You just have to know that your data is not perfect because you're dealing with people who aren't perfect, and you're dealing with things that are going to change. So data is always an estimate. So be aware, it's never perfection. It's always an estimate. Statistics is you work really hard to estimate. And that's why nothing's ever guaranteed. Just know that. So that is 1, 2. Let me know if you have any questions.